Hello everyone, and in today's lecture I'm going to discuss how to design controller or regulator design So in other words, we are looking how to design the regulator such that the given plant controller such that the given plant in the feedback structure given as it follows. This is the classical feedback structure, is stable. So given some R of t reference signal that we compare with the measurement from the plant, the question is that how do we design a regulator or controller such that the closed loop system is stable. In the previous lecture we know that plant dynamics is xp dot equal ap plant xp plus bp plant up y plant cx plant. In the same way, for the plant we can have a transfer function representation that the g of s of plant is going to be C plant Si minus A plant inverse B plant, such that we can look that this plant here has a certain transfer function, and the controller can be given as well as a ACXC plus BC U of C. Y of C is equal, here is CP, CCXC plus DC U of C. And this controller also can have a G controller transfer function, which is DC plus CCSI minus AC inverse BC. In other words, we can look at the classical representation in a transfer function style representation where G of C is here and just G of the plant is given as follows. Okay, and we have that, and we recognize this is just our classic representation of the feedback control structure. Having this in mind, we also claim that from this state space representation we had a closed loop system is A plant 0 0 0 plus here B plant 0 0 0 DC controller, CC controller, BC controller, and AC controller. I need to make a small correction here. this term here, it's identity, it's not zero. Here is identity, and this has been demonstrated in the previous lecture. And here we have a CP 0, 0 identity. As we said previously, this is like some A hat here plus some B hat gain. Look, K matrix, it's a gain multiply some C hat, such that we can almost see that there is already some structure of the state feedback, that ACL, which is ultimately the matrix that describes the internal stability of the closed loop system, eigenvalues can be perturbed with this gain K. In other words, the controller has a 2 degrees of freedom and C order of the controller. And second thing is a gain of the controller, or AC, BC, CC, and DC. So these two parameters are two parameters that we can use in order to explore and to ensure that regulator stabilizes the system. Okay, and what do we have if we just think about just simple gain-based controller? Because we can use just simple the gain, constant gain, as a first option. So if K is just gain, no dynamics, gain, and C is equal to 0 order. So controller does not have dynamics. We get just the following picture. R of S plus some gain K, G of S. Okay, this is already something that we are familiar with, because we know that stability of this system is defined by the closed loop transfer function characteristic equation, and the characteristic polynomial of the closed loop transfer function is the following: 1 plus K G of S. Okay. In other words, we have a gain, this is equal to 0, we have a gain that ensures that the solutions or the roots of this P of S characteristic polynomial are negative. In other words, P of S also can have the following expression: D of S plus K of S N of S, providing that D of S and N of S are co-primes. So this is equal to 0, are co-primes. Co-primes. What does it mean, co-primes? They don't share a common factors. Therefore, for the given gain, you fix the gain, you solve characteristic polynomial, and one obtains in the complex plane the following distribution of the eigenvalues. Let's say one pair of conjugate complex and one is real. So this is lambda 1, this is lambda 2, and this is lambda 2 conjugate complex. In other words, as gain is changed, this K, which is gain, is changed. This is for the fixed gain. These eigenvalues will move, for example, will migrate, and it can cross the imaginary axis, so there is some instance of the gain, okay, where these eigenvalues are crossing the axis, and these eigenvalues become from negative positive, which means the system becomes unstable. In other words, this one can cross the following way. So if this is for k equal 3, for example, this can happen for k equal 100. Therefore, obviously, we know that gain has to be less than 100 in order to keep the distribution of the eigenvalues in the left side of the complex plane. That is the way how one can access the eigenvalues distribution, which is or roots of characteristic polynomial, as it is parameterized by k, because k as a simple gain just changes the value from 0 usually also to infinity. Okay, so this is what gain, and it's intuitively easily to understand that this just gain for the certain value will place the eigenvalues of the closed loop characteristic polynomial at certain places in the left complex plane. Now, let us look for the example where we have, so just example, where we have the following plant, and we have a gain-based controller. So just simple gain, how we are going to ensure the closed loop system stability, and let's assume that the transfer function is 4s plus 1 divided by s squared plus 2s plus 3. Okay, we already noticed that this is classical closed loop system representation. This is plus, this is minus, and characteristic polynomial is the way to check the stability. In this case, we have that s squared plus 2s plus 3 plus k 4s plus 1 equals 0, and after we group the factors and coefficients, we have 2 plus 4k s plus k plus 3 equals 0. From the Hurwitz criteria, we can inspect the coefficients of the characteristic polynomial and find out if the system is stable, and sufficient condition is there is no sign change in the polynomial and the coefficients in the Hurwitz table not to change the sign. So if this is the polynomial, the Hurwitz table is built as follows: S1, S0, and here we write A2, A0, A1, 0, and here is A0. Okay, so these terms should not have a change of sign. And given that, we have, for this case, that the Hurwitz table will be 1k plus 3, 2 plus 4k, 0, and k plus 3. Okay, this implies that we will have k greater than -1 by half and k greater than -3. Therefore, the gain that will successfully stabilize the system, it goes from -1 by half to infinity. Okay, any k that we pick up will provide the closed loop system stability in this case. Okay, now I'm going to keep the same plant. I'm just going slightly to change here the sign because I don't want that plant is a stable. So let me change the sign. So here it's negative, and I will put with the yellow color just for the second case to show you and demonstrate, can we find a gain such the system will stabilize be stabilized by the pure gain based controller. In this case, just P of S is going to change. So let's write the P of S, new P of S. And in this case, P of S is going to be S squared plus 4k minus 2s plus 3 plus k. Okay. Again, for the Hurwitz stable, we have s squared, s1, s0. We will have here 1, 3 plus k. We will have a 4k minus 2, 0. And we will have 3 plus k. Okay? Which implies that we will have k greater than 1 by half, and we will have a k greater than -3. As you can see, the range of the available gains that can stabilize the closed loop system in the case when the original system is unstable, like in this case, it's already smaller than the previous example. So here we have that k is going to be all values from 1 by half to infinity. So the gain, still pure gain, 1 by half to infinity. Okay. Interestingly enough, still we are doing with a simple gain. Okay, let us now look for the more complex case, but complexity is not going to be tremendously different or change from what we have, but I'm just going to remove this stable 0, and I'm going just to place here unstable 0. Let's look what we have there. This is the third case. So in this case, what do we have again for the P of S? Okay, P of S in this case is going to be s squared minus 8s plus 2 plus k 4s minus 1, and I just need to change these to be 8s, and this has to be 2 now. So slightly different transfer function. Okay, So this is minus 8s plus 2, that's the term that is coming from here. Multiply k, multiply 4s minus 1, that's what we have. Such that s squared leads to the following conditions, that we have a s squared plus 4k minus 8s plus 2 minus k equals 0. What I constructed in this case is the following. I constructed that condition has to be now the same way like from the curvature table, 4k minus 8 greater than 0 and 2 minus k greater than 0, which implies that k has to be greater than 2 and smaller than 2. Obviously, no k exists. In other words, we demonstrate that in this case, there is no gain that can stabilize, no gain that makes stable closed loop system. Closed loop system. What do we do in this case? Obviously, we completely explore the case of the pure gain. And now we have to get back to our initial case and increase the order of the controller, because NC was 0 and we are going to increase the order of the controller, and we are now going to put the first order controller. What is the first order controller? Now G of C is something that is going to be alpha 1s plus alpha 0 s plus beta 0. So this is the first order controller, okay, which allows us to have more parameters, alpha 1, alpha 0 and b0, such that we can utilize and ensure the closed loop system stability. What do we have now? Let's write the P of s in this case. This is s squared minus 8s plus 2 multiplies denominator of the controller s plus b0 plus alpha 1s plus alpha 0 4s minus 1 equal 0. Therefore, this is the characteristic polynomial in this case. And if we group the terms in the characteristic polynomial, we will have a s cubed plus beta 0 minus 8 plus 4 alpha 1. You can easily multiply all of this and find out that terms will be grouped in these structures. Minus 8 beta 0 plus 2 plus 4 alpha 0 minus alpha 1. This is next to the s term, and the last term is 2 beta 0 plus, minus alpha 0, that's all equals 0. Okay, now as we know that all of these terms have to be positive, we can assume and choose the stable characteristic polynomial. In other words, I will choose some A2, I will choose some A1, and I will choose some A0. For example, my favorite stable polynomial is s plus 1 cube, such that these terms are just 1, 3, 3, 1. I know A0 is 1, A1 is 3, A2 is 3, and this term is also 1. Okay? And this is the stable polynomial. In other words, final solution to this problem is to solve the linear system of equations such that we have that B0 minus 8 plus 4 alpha 1 equal A2, that we pre-specify, also minus 8B0 plus 2 plus 4 alpha 0 minus alpha 1 equal A1. Okay, and the last one is 2B0 minus alpha 0 equal again A0. This will be pretty much like some A matrix. We will have a parameters here, alpha 0, alpha 1, beta 0, and here we will have a A2, A1, and A0. Okay, in this way we're just solving the system of linear equations, and this system, it's trivially solvable for us. In other words, in the case when we could not stabilize with a gain, we had to increase the order of the controller to provide the new set of parameters given here, such that we can guarantee the closed loop system stability. In general, this is the always procedure that we do when we designed the controller.